Hello again. So this is structural analysis made fun and easy. Please like the video and subscribe to the channel. We're going to do a single span beam with two small cantilevers, and we're going to look at the moments and the loadings. And this question is really the relationship between loading on the beam, bending moments, and the resultant bending stresses on the section. So we're also going to look at moments of inertia, which I've covered in another video, and stresses resulting from bending moment, which is engineer's theory of bending. So the question states that we've got the overhanging beam, this is as shown, as I've drawn out, is subjected to a uniform distributed load over the entire length of the beam. The sectional properties and dimensions of the beam are given below also. So I've done them as section AA there, but a bit further down, so we don't need that quite yet. So the overhang beam is subjected to UDL over the entire length, which is the blue. The sectional properties and dimensions of the beam are given below also. So the important bit of the question says, for the beam material, if the allowable bearing stresses in tension and compression are 30 newtons per millimetre squared and 70 newton per millimetre squared respectively, determine the maximum uniformly distributed load that can be applied to the beam. So just to clarify, so we've got this single span beam. The single span is 4 meters, and then we've got an overhang cantilever of 1 meter on each end, so it's symmetrical about the middle point, and it carries a UDL of W per unit length. So just call the positions A, B, C, D, and cantilever on each end, 4 meters internal span. Section AA, I'll show you that further down. That's the section. That's where we've got this. We know the cross section. They've given us the section properties, and that's the neutral axis, and the second moment of area. So just a quick note about this question. So it says the stresses allowable in tension and compression are 30 newtons per millimetre squared and 70 newton per millimetre squared. So basically this means that in tension it can take 30 newtons per millimetre squared, and in compression it can take 70 newtons per millimetre squared. So this sounds correct for a concrete section, because concrete could take a smaller stress in tension than it can in compression. So 30 newtons per millimetre squared tension, bigger than 70 newtons per millimetre squared in compression. So that sounds about right for the concrete section. So basically we know that this beam can carry 30 newtons per millimetre squared in stress on the cross section in tension, and 70 newtons per millimetre in compression. So what we need to do is find out, first step, let's determine where the maximum design moments are in the beam, so we can find out they must be where the greatest stress is, where the maximum moments are in the section. So if you ask me from experience, I'd say wherever the bending moment is going to be bigger, going to be in the middle of the span and at the support. That's where we need to check. So I reckon let's start by determining the maximum design support moment in the beam. So Dan just drawn out a little diagram for the cantilever section, so it's symmetrical. So this is just, one's right hand side, one's left hand side. This one's the right hand side. It's going to be symmetrical for the left hand side. So we've got, as shown in the WC, is the total the total load of the UDL over the cantilever. So the orange bit, that's just the same as the blue bit that I drew. It's all over the entire beam, but I've drawn it in orange just to show it over that, so it's highlighted over the cantilever, but it's basically the same as the blue all the way through. So and the span, oh yeah, so we've got here the length of the cantilever, that is 1 as given above. Here, so the equivalent point load is the sum of the entire UDL over the length of the cantilever at the centre of the load at the centre of the UDL load. So the centre of the UDL load is 1 divided by 2, which is also the lever arm. When we take moments about when we take moments about C here, the support is C. The support is C. That's the we can use that to find the moment. So as I've shown here, the UDL W in this box, the UDL W over the entire length of the beam, including the cantilever, that's W. But it doesn't say anything about the self weight, so I'm not going to include that in this one. The length of the cantilever is 1, call it LC. The lever arm, that's that distance from the centre of load to the support, that lever arm distance from B to the centre of the, that should be C. From C to the centre load of the cantilever is 0.5 metre. WC, the total load, the total of the UDL load over the length of the cantilever, WC, LC times W is 0.5 times W is 0.5 W kilonewtons. Oh, sorry, it's 1. That's 1, it's 1 W. Obviously, WC is the total of the UDL over the length of the cantilever. WC times LT times W is 1 times W. So the moment at B should be the moment at C. The moment at C. Moment at C at the support is equal to that W times the lever arm, and the lever arm is LC over 2, which is 0.5. That means it's 1 W times 0.5, which is 0.5 W, which is W over 2. So we've done the equivalent point load times the lever arm. That gives us M at the support. So basically you get a bending moment diagram, triangular, 0 at the edge of the cantilever, and then it's obviously highest at the support with a total maximum value of W over 2 kilonewton meters, and it's clockwise direction on the right hand end and anti-clockwise from the left hand end. So that basically means we've got the bending moment at the supports C and B. So the second step is to, now we need to know what the bending moment is in the middle, the sagging moment. So what we need to do first of all is we need to determine what the reactions are, the support reactions RA and RB. So let's go back to our basic methods. I've already done a couple of videos on how to resolve. We've got statically determinant. This beam is statically determinant because there's 2 reactions, but there's 3 equations. There's two reactions, but there's 3 equations. So let's start by taking the vertical reactions. RA plus RB must equal to W times the length of the entire length of the beam. So RA plus RB minus W times 6 equals 0. Rearranging this, RA plus RB equals 6W. So now we need to find the reactions. So let's take moments about RA. So we got this part of the this part of the UDL, that's 5 meters long, 5 meters times the lever arm is 5 over 2 plus 4 times RB, which is this lever arm here, 4 meters times RB, going anti-clockwise, and then this little bit of cantilever on this side is also going anti-clockwise about A. So we got 1 times W times a half, which is the lever arm of that. The UDL over the cantilever that's half. So we rearrange that equation. I'll just make that a bit bigger so you can see. That's 5W times 5 divided by 2. That's the entire UDL on the right hand side of support A, which is 5 meters long, 5 meters of W, and then the lever arm is 5 meters divided by 2. That is clockwise, plus 4RB, because it's anti-clockwise, plus the 1 times W times half. So we rearrange this equation, we got 4RB is equal to 12.5, that's 5 times 5 over 2, 25 over 2, 12.5, and 12.5W minus 0.5W. 4RB is therefore 12W. Therefore RB equals 12 over 4W equals 3W kilonewtons. Then we just plug that result back into equation 1, and we get RA equals 6W minus 3W equals 3W.